Namaste and welcome to this lecture on mathematical foundations for machine learning. We are in the process of learning the ideas of calculus. We just did one lecture on the idea of derivatives and we looked at Taylor series expansion for the function e power x. Of course, one more example what we can take is like we will look at one more example of Taylor series now, and then we will get on to the ideas of rules of differentiation. So, what are the rules that are involved and chain rules? So, that will be the focus of this class. When we come back in the next class, we will have more interesting topics to come. So, what we are going to do now is we are just going to have a quick recap of a Taylor series, and then we are going to look at something interesting. And I would also expect you to work on a couple of problems on this Taylor series, right? Okay, so recap. Given a function f of x, given a function f of x, what we are going to do is we are going to look at the power series expansion for the Taylor series expansion. Let us say the Taylor series expansion of course, we have to look at the idea of convergence, which I have not touched upon. That itself is like a pretty big topic. So, what we will do is we will just look at functions for which we have the Taylor series right now. So, we will look at that. So, the Taylor series expansion of f of x at a point x is equal to say x naught is given by f of x is equal to f of x naught plus f dash of x naught into x minus x naught plus f double dash of x naught by 2 factorial into x minus x naught the whole squared, and so on. In a compact form, you can write this as f of x naught plus I will use this f k to denote the kth derivative of x naught in by factorial k. This is 1 to k is equal to 1 to infinity x minus x naught power k, right. So, this is going to be the Taylor series expansion. You can see that if I put k is equal to 1, this says f power 1, that means that is the first derivative. Then if I say f squared, this is nothing but the second derivative of x naught by 2 factorial into x minus x naught the whole squared, and so on. Now, recall we also did something interesting out there. What was that? We said that e power x, the Taylor series expansion for e power x was the following: f of x is equal to e power x. The Taylor series expansion was basically 1 plus x squared by factorial 2 plus x cube by factorial 3 plus etc. and so on. This is what we had, right. 1 plus x squared plus x squared by factorial 2 plus x cube by factorial 3 and so on. Now, I just want to make a small change here. I want to look at not just f of x, I want to look at f of e power f of I x, where I is the complex variable that you take. So, I am going to look at f of let us say I x, complex number. So, I am going to look at this is nothing but e power I x, right. This is going to be e power I x, or I am just going to look at the power series expansion for e power I x. So, let us put that e power I x is nothing but 1 plus I x plus I x the whole squared by 2. So, I is the complex, so you basically have the complex function. So, I squared is minus 1. So, you have this. So, this is basically e power I x, and we know what is e power I x, we will come to that. So ix by 2 factor ix the whole square plus 2 to then ix the whole cube by factorial 3 and so on. Now what is that? We know that I squared is minus 1, so we are going to use that fact here. So this is going to be 1 plus ix. Let me just do this. I am going to write this as 1 plus ix, then I am going to have minus, this is going to be I squared which is minus 1. So I am going to write this as minus x squared by factorial 2. Then what I am going to have is I am going to have I squared is minus 1, I cube is minus I. So this is going to be nothing but minus I x cube by factorial 3. Then I am going to have plus I squared is minus 1, I x the whole power 4, I squared is minus 1, so I power 4 is plus 1. I am going to have plus x power 4 by factorial 4. Then I am going to have minus I x cube. Now I have I x power 5, which is nothing but plus I x power 5 by factorial 5. I am going to have something like this minus and so on, right. Let us do a small interesting stuff here. What is that I am going to do? I am going to write this as, I am going to collect all the real terms together and then the complex term I am going to put them together. So I am going to have 1 minus x squared by factorial 2 plus x power 4 by factorial 4 minus x power 6 by factorial 6 plus so on plus I into x minus x cube by factorial 3 plus x power 5 by factorial by 5 factorial minus x power 7 by factorial 7 plus and so on. Now why did we separate this way and what are we going to get out of it? That is interesting. Let us look at e power ix. When we say e power ix, all of us know that this is nothing but cos x plus I sin x, right. E power ix is cos x plus I sin x. Now what we have is exactly the same thing that we have here. There is something that goes here plus I times something that goes there. So what we see is this is basically the Taylor series expansion of the function cos x, and this is going to be the Taylor series expansion for the function sin x. So what we have cos x plus I sin x is what we have. In fact, I would leave it as an exercise to all of you. Try this out, try to get the Taylor series expansion for, in the method that we did in the previous class, try to get Taylor series expansion. Taylor series expansion of cos x and sin x, right. You can do this, I mean evaluate the function at x is equal to 0. So basically Maclaurin series you are trying to find out. So what to do is Taylor Maclaurin series, let me put, you can evaluate this at x equal to 0 and you will arrive at the same thing that we put here, cos x and sin x. That is pretty interesting, right. So we also thought, we also looked at the generalized Taylor series expansion. Now what we are going to do is, moving on, we are going to look at some of the rules for differentiation. We are going to look at the rules for differentiation. Now why do we need this? Say suppose I have two functions, f of x and g of x. Let us say that I have two functions, let f of x and g of x be functions. Now I am going to combine these two functions and then get, let us say, another function, let us say h of x is equal to f of x plus g of x. I want to find out what is the derivative of this function dh, which is nothing but the derivative of f of x plus g of x. right. This is what we have. Now what is this going to be? This is nothing but, you can write this as f of x plus h plus g of x plus h minus f of x minus g of x. So it will separate out very nicely and you will get this as d by dx of f of x plus d by dx of g of x, which is nothing but the derivative of the x with f with respect to x plus the derivative of g. So what does it say? It says the derivative of a sum of two functions is nothing but the sum of the derivatives. This is something which we have seen before. Where have we seen this? Remember, when we did linear transformation, we said that the transformation acting on, you want to find out what is the, you suppose if T is a linear transformation, I want to look at what is the transformation on, let us say, alpha x plus beta y, these two are vectors. What did we say? We said that this is nothing but alpha times transformation of the x vector plus beta times the transformation of the y vector. Suppose if alpha and beta were equal to 1, then I am going to look at what is the transformation, linear transformation of, what is the effect of the linear transformation on the sum of two vectors. This is nothing but the sum of linear transformations, or the you are going to say that transformation on x, whatever vector you are going to get, you are going to write this as transformation on y. Therefore what we see is the differential operator that you have, you see that it is actually a linear operator. It is a linear operator that we have, right. So in fact you can capture the idea of differentiation in terms of matrices also. Will, for the time being, will not look into it, okay. So this is the first one that we have. So the derivative of a sum is equal to sum of the derivatives. The second most important property that we are going to look at is, suppose I have h of x to be defined as the product of two functions f of x into g of x, f of x into g of x. So how are we going to look at the derivative of h with respect to x, which is nothing but d by dx of, let us say, f of x into g of x. So we saw that the derivative of the sum is equal to the sum of derivatives. Now we want to see what is the derivative of product. Is the derivative of product the product of derivatives? Well, that seems to be pretty interesting if we have something like that. So let us put a question mark here. Is it equal to f dashed of x into g dashed of x? We do not even know. If that were to be the case, life is very easy. Derivative of sum is sum of derivatives, derivative of product is product of derivatives. No, of course we have to check what is going to happen. So let us just do our basic way of finding the derivative. So I am going to look at d h by dx is nothing but limit h, okay, let me make some other variable here, limit t tending to 0 or limit delta x tending to 0, because okay, let me make limit delta x tending to 0. I am going to have f of x plus delta x into g of x plus delta x minus f of x into g of x divided by delta x. This is what I have. This does not take us anywhere, like, because we are in the same state as where we were before. So what I am going to do is I am going to add and subtract f of x plus delta x into g of x in the numerator. Now what are we going to get? So this is nothing but limit delta x is tends to 0. I am going to have f of x plus delta x into g of x plus delta x plus f of x plus delta x into g of x minus f of x plus delta x. Effectively the terms become, these two cancel out and it becomes 0. I am just going to add these two things, minus f of x into g of x, right. This is what we have divided by delta x. So, this is nothing but limit delta x tending to 0. So, what am I going to do? I am going to take f of x plus delta x common, and I am going to take this as f of x plus delta x into g of x plus delta x minus g of x, plus I am going to take g of x plus g of x, I am going to take it out, I am going to take g of x out into f of x plus delta x minus f of x divided by delta x. Oh well, we know that now you can separate this out as two terms. The first term you can take it as two terms, the first term and then the second term, you can take them out. So, what we see with the first term, as far as the first term is concerned, what we see is the following. What is this? This alone, if you see, I will just put a box here. This is nothing but my g dash of x, the derivative of g function, and if you look at this, if you look at this, this is going to be f dash of x into g of x. Oh, something interesting happens here. So, what is this? Derivative of a product of two functions f of x into g of x is nothing but f of x into g dash of x plus f dash of x into g of x. So, we asked a question, is the product is the derivative of a product equal to the product of derivatives? Sadly it is not. So, we are going to say that this is not equal to this. So, the question that we had, we are going to say, look, do not do this mistake, it is not going to be equal, right. Of course, you have your quotient rule and so on. What we will do is, like, we will not look at those, but we want to focus on something more important. Let us just make a mention of the quotient rule here. So, the quotient rule if you want to take the derivative of f of x by g of x, you can actually do it, you can do something similar to what we have done before. You can do this, and this would boil down to g dash of x into f of x minus f of x into g dash of x, sorry, g of x into f dash of x minus f of x into g dash of x divided by g of x the whole square, right. This is what we have. So, we saw that we saw three important rules of taking derivatives. Derivatives of the sum is sum of derivatives, derivatives of product is not that easy to calculate. It is basically the derivative of product f g is nothing but f into g dash plus f dash into g, and we also saw the derivative of f by g is nothing but g into f dash minus f into g dash divided by g squared. So, that is what we have. But one of the most important rules for derivatives is basically the chain rule, which is what we are going to see now. So, this is chain rule of derivatives. This is basically the chain rule for derivatives, which is very important, right. Okay, let us see what does this actually mean. Suppose I consider this function, consider let us say f of x is equal to let us say cos x squared, cos x squared, where I am going to say g of x, I am going to put this, I am going to say look, y is equal to g of x is equal to x squared. So, what am I going to have? I am going to have f of x is equal to cos of, basically it is not, it is basically this, it is f of g of x that I have, f of x is cos of g of x I want to put. So, what I will do is f of g of x is nothing but cos of g of x, which is nothing but cos x squared. I am going to have this, right. Oh, that is great. So, what am I going to do? So, I am going to take the derivative. How do I take this derivative now? It is a cosine. So, you basically take the cosine of a function, cosine of the argument. The argument is basically a function of another variable x squared, right. So, what I am going to do is I am going to call this f of g of x as, let us say, the function z. This is going to be equal to, say, some z. So, now what I am going to do is I want to look at, I am going to give a name for this, z is equal to f of g of x, z is equal to f of g of x is basically called as a composition, is called a composition is called a composition and denoted by f dot f, this whatever bullet you have, or a circle of x, right. This means it is f of g of x, and what is interesting in this case is the order of the function, the order of f and g is very, very important. See, the order of f and g is important, okay. So, let us take this, we had this like f of g of x cos x squared. So, let us see what is g of f of x. So, we had f of g of x to be f of g of x is given by cos x squared, right, cos of x squared. Now, what I am going to do is I am going to look at g of f of x. G of f of x is nothing but f of x is cos. So, I am going to look at the argument of that with respect to, so g of this. So, what am I going to get? G of f of x. What is f of x? F of x is nothing but cos x squared. F of x is nothing but cos of x. So, let us take this. So, this is nothing but cos x the whole square, right. Let me take, okay, let me put this as f of, let me just do this. Okay, this is fine. So, there is a difference, but this is nothing but cos squared x. So, of course, you see that this is the cosine of the squared of x and this is going to be cosine squared of x. So, these two are basically different, right. So, we have this. So, we see that the order of the function does matter, and yeah, so essentially you do not need to have f of g to be equal to g of f, right, you do not really have to do it. Now, what you do is, suppose I want to look at what is the derivative of a composition. Let me look at the derivative of a composition. Derivative of a composition. let us say f of g of x, right. I have this. So, let us say z is equal to f of g of x. Let me make a small substitution here, let g of y be equal, let me g of x is equal to y. So, what do we have now? We have z is equal to f of y. We have z is equal to f of y. Now, what is dz by dx? What is the derivative? I want to find out the derivative of z with respect to x, because ultimately that is what is here. This is nothing but, I can take this as dz by dx is equal to, z is a function of y. So, I am going to say dz by dy and into dy by dx. So, that is basically what you have as your composition. Oh, brilliant, something interesting comes out here. What is this? If I want to look at the derivative of a composition, it turns out that this is going to be a product of the derivatives, which is nothing but, I am going to take this as f dash of g of x. That means it is with respect to g of x into, I have g dash of x. What we have, we will just take an example and we will be understanding it better. So, let us consider this example where the function z, I am going to look at it, the z function is nothing but sine of square root of x plus 1, right. It is going to be square root of x plus 1. So, what I am going to do is I am just going to take y to be equal to square root of x plus 1, y to be equal to square root of x plus 1, and or let me say y is equal to, I will put it in a better way. So, I will take y is equal to square root of u, and I will take u to be equal to x plus 1, right. I am going to take y is equal to square root of u and u to be x plus 1. So, what do we have? We have z is equal to sine of y, which is nothing but sine of root of u, which is nothing but sine of root of x plus 1, is what we have, right. Y is equal to root u. So, I put root u there and u is equal to square root of x plus 1, and where u is equal to x plus 1, right. Okay, great. So, now what I want to do is I want to figure out what is dz by dx. Ultimately, it is all the function of x. So, I want to find out what is dz by dx. dz by dx is basically z is a function of y, y is a function of u, u is a function of x. So, what I am going to have? I am going to have dz by dy into dy by du into du by dx. Ultimately, you get your dz by dx. So, what is dz by dy? dz by dy is nothing but cos y. What is dy by du? dy by du is nothing but differential of square root of u, which is nothing but 1 by 2 root u, right. And what is du by dx? That is 1 into 1. So, what do we have? We have the derivative to be cos y into 1 by 2 root u into 1. What is y? Y is nothing but, so I am going to have, this is nothing but cos into square root of x, cos of square root of x plus 1 into 1 by 2 square root of x plus 1 into 1. So, that is the derivative that we have. The derivative of the composition is basically this. Where do we see this? As I said, when Dr. Ashok Rao deals with back propagation algorithm, you would see the use of these chain rule and stuff, right. So, this is a very, very important topic as far as the derivation or the derivatives and the rules of derivatives are concerned. What we will do is we will wind up with this in today's class, and when we come back for the next class, we are going to get into the most important topic which we have been waiting for as far as this week is concerned. We are going to look at partial derivatives. We are going to look at the idea of partial derivatives. Okay. So, in this class what we did, we basically looked at an example of Taylor series, where we looked at the Taylor series expansion for the function e power I x, and then we looked at the rules for differentiation, we looked at sum rule, product, and then quotient. And the most important thing that we saw was like the sum of the derivative of the sum is equal to sum of derivatives, whereas derivative of products is not equal to the product of derivatives, and we looked at derivative of numerator by denominator, and we also looked at one of the most important results, which is the chain rule. So, when we come back in the next class, we are going to look at partial derivatives and some kind of introduction to this idea of partial derivatives, where we are going to look at a surface plot, we are going to look at some surfaces and so on, and then we get into the notion of partial derivatives and chain rule. Namaste.